Now let's have a look at how a common Pelton wheel, or as a Pelton wheel is a part of an impulse turbine, how they are being installed in a hydroelectric power generation. So before we begin to discuss about the head and the losses that occurs in the systems, let's get to know what are the components of a common hydroelectric power generation that based on Pelton wheel. So now let's say here this is for Pelton wheel. So here we have the Pelton wheel itself, and this C-shaped geometry is what we call as the bucket. So bucket receive the energy from the water, and then before we go to that, and we have the upper reservoir that collect the liquid working fluid. In this case is the water, and then after leaving the reservoir, the fluid will flow through this area that we can call as the pressure tunnel, and then after that it will go through to almost a vertical pipeline. Here we call this as penstock, and then it will flow into the smaller area. At the end of the pipeline of the penstock we have the nozzle. So the nozzle here will spray the liquid and hit the bucket here, causing rotations, and then it rotates the generator to generate the electricity. That's in a simple way how the electricity being produced in a common Pelton wheel hydroelectric power generations. And then one other thing that we need to know is this small reservoir that called as the surge tank. So surge tank is basically to maintain the pressure distributions in the pipeline systems so that there will be no, let's say, shock wave or the immediate rise in the pressure inside the pipeline from the pressure tunnel to the penstock. So if there's any pressure increase in the flow to the Pelton wheel, this level of liquid will rise to avoid this sudden pressure rise in the pipeline system. Now that we already know the components, first we have the reservoir, pressure tunnel, then we have penstock here. Now we need to have a look at the parameter that we will deal when we need to analyze the performance of an impulse turbine. Now H1 here, it's represent the available head. So this is the head that being available in the installations of hydraulic turbines. And then because we have some pipelines and connections and so on that causing losses, so the losses due to the pipeline and let's say connections between pipes and connections, and we can also count due to frictions that might cause an energy loss. We call it as small hf, and this is normally will cost us around or between 5 to 10% of energy losses due to pipeline connections, frictions, and change in the cross-sections area of the pipeline. And now due to HF, we have the head become H here. So H is H1 minus H fluid. So make it too clear. Another head is what we have here is the H prime, or in Bahasa we call it H accent. So this H prime represents as the effective head. So the effective head is represent the amount of head that being delivered to the turbine, and this is one of the costs is due to the nozzle here that might cost us 1 to 2% in energy losses. So we have H prime, and on the other hand, when we design the turbine, the points that we need to consider is normally the power, or let's say P with unit in watt, and we also need to consider flow rate, Q with unit in cubic meter per second, and head, H with unit in meter, the rotational speeds of the turbine with unit in RPM. And when we want to select the turbine, or which type of turbine or which type of Pelton wheel that we will use, normally we will have a look on the specific speed, or NS. The specific speed of the turbine or Pelton wheel in this case is represented or can be estimated through the equations that is a functions of the rotational speeds of the turbine multiplied with the power to the power of 0.5 divided by density to the power of 0.5 multiply with gravity with head to the power of 5/4. On the other hand, when the fluids leave the nozzle before it hit the bucket here, so when it flows here due to the decrease in the area, the velocity is getting higher, and then at the end it will hit the bucket to create the rotations here. The velocity of the fluid leaving the nozzle, we normally call it jet. So theoretically, the velocity of the jet, let's say jet velocity, I mean this is the theoretical one, is equal to the square root of 2 times gravity times head. This is the theoretical one. However, we have, as I've explained before, there is losses here on the nozzle that we call as the velocity coefficients. Then the jet velocity, this time is the actual one, becomes velocity coefficient multiplied with the square root of 2 times gravity times head.